Sure. Welcome, everybody. Today's speaker is someone you all, I think, know, Josh Kroll, who is a graduate student here in Computer Science Department and CITP, and he's going to talk about accountable algorithms.
Hi, everyone. Thanks, Ed, for the introduction, and thanks to all of you for coming out on what is a pretty snowy day here in Princeton. So I'm here to talk about accountable algorithms, and when I say algorithms in this context, I'm really talking very specifically about processes for automated decision-making. You might think that such processes are rare. By automated, I mean decision-making processes that follow a rule, as opposed to being based on the discretion of a human sitting behind a desk with a lot of paper on it wearing a thin black tie. And you might think that these processes are rare, but actually there are a lot of automated decision processes, automated in one form or another, ranging from systems that calculate scores for credit or insurance underwriting to systems that help figure out what resumes should, based on resumes that are submitted to an employer, which candidates are most likely to be successful in an interview. In the case of a lot of these systems, there has been some skepticism in terms of, are they fair? Do they do what we want? And so when I say accountable, I mean that the social or technical, social or legal or political processes that are supposed to govern these systems operate in the way that they should. That means that both that the rules are being followed and that the rules are fair and that the rules are just. This is a photo of the top of the Supreme Court building on which is written the phrase "equal justice under law." It's a legitimate question, I think, because the processes for oversight of these systems really are based on the notion that decisions are made by that person sitting behind a desk looking at a lot of paper. If you look at this problem and you're a lawyer, you say the solution that we need is transparency. And by transparency, I mean that everybody knows what's going on in the system. For an algorithmic decision, that means that everyone has the code for the system that's making the decision, and everyone has the input data which were given to that code to make the decision. This isn't always what you want, because there are legitimate reasons sometimes to keep a process secret. If you think about the algorithm that generates your credit score, the credit rating agency doesn't want to show you that because they don't want you to arrange your affairs so as to get the highest possible score. They would like to give a score that maximizes the utility of their customers, which are lenders. And then you can't imagine in a lot of cases that it's a good idea to give everyone access to all of the input data, as there might be some privacy issues. And also, transparency is not always a sufficient solution. For example, if an algorithm is randomized or interacts with its environment in a way that you can't predict, it's difficult to come back later and reconstruct exactly how that code ran and what it did. And so I want to say that accountability is not the same thing as transparency. Transparency is not going to get you all the way to where you need to go if you're looking for full accountability. If you're a computer scientist and you look at this problem, your first instinct is, well, we should get some property that we want the system to have, and we should prove that the system has that using some sort of technical assurance mechanism. That could be as simple as running some tests. It could be as complicated as formally specifying the property you want it to have and formally proving that some piece of software actually satisfies that specification. However, political social processes tend to be compromise-based, and therefore the rules that are generated by humans tend to be vague almost by design. So it's not really possible to know what is supposed to happen in a coherent way in a lot of these systems. We're not going to get, or we shouldn't expect to get from a political process, something that resembles at all something that a computer scientist would call a specification. And then, even if you did have a specification, you have the problem that you don't know that the system that you are using in practice is the same system that satisfies the specification. And so you have a problem of connecting whatever technical assurance you have about the specification that you came up with, such as you can get one, to the actual thing you're using in practice. And so accountability is not the same thing as formal proof of some desirable property. So I'm a computer scientist, and I'm talking today about some computer science that we're doing here at CITP. So what do you do as a computer scientist if you want to approach the problem of how do we make automated decision processes accountable? I want to talk about two pieces of work today. In both pieces of work, there are two key assumptions. One is that secrecy is a valid, useful concept that we should allow in processes that run in the real world. We want to keep some things secret from some people. The other thing is that the social and political and legal process is not going to give us a precise theory of how to differentiate acceptable behavior for a system from unacceptable behavior for a system. And so instead, we're going to use a trick in computer science. We're going to model the decision about whether some behavior is acceptable or unacceptable as an oracle. So we're going to say this is a function, we don't know how to compute it, but there is a well-defined specification out there. We just don't know what it is, but we might be able to ask for the particular cases that we care about. And that opens up a couple of technical approaches to getting accountability. One of which is, I know I just spent a bunch of time saying that you don't always have this, but when you do have a precise specification, or you do know what property you want the system to have, you can ensure that you have accountability before the system goes into production by proving statically that you actually do have some policy which is correct, and for the computer scientists in the room, you can think of this as a kind of static analysis. And the other approach is a kind of dynamic analysis, which is to ensure accountability after the fact via a mechanism that I'll explain later, which we call oversight. And the idea in the oversight mechanism is that you can take a dynamic check of some property you want and say, not only can we check this, could we check this when the system is running, but in fact we can bundle up that check and defer it until later. And if I can convince you that I could do the check later, then you should trust that if there's some sort of dispute, we can bring that deferred check in front of a court or the Senate committee on whatever the system is, and that check can happen there, and at that point we can figure out what was actually supposed to happen. And to give a more precise sort of computer science-y definition of accountability, as we move more into the computer science of this, I want to say that accountability is proof to a skeptical third party who's not involved in the system that there's a full explanation after the fact of what happened in the system, and that the behavior covered by that explanation was the desired behavior of the system. And a third party who believes these two things will find the system to be trustworthy enough to believe that it's accountable to whatever human level process is supposed to be governing it. And so today I'm going to talk about two systems. One is a system for the accountable execution of legal warrants, which is an example of the sort of correct by construction, we know what the spec is beforehand type of oversight, or type of accountability. And the second piece of work I'm going to talk about is accountable algorithms, is what we call it, and that's this new sort of after-the-fact deferred check based on oversight system. So without too much more introduction, I'm going to dive right into the accountable warrants work. I should mention before I start that this work is joint work with a bunch of cryptographers, David Wu, Joe Zimmerman, Valeria Nikolayenko, and Dan Benet, who are all at Stanford. And before talking about this work, I want to talk a little bit about the problem of executing a warrant. So we have people out in the world, citizens out in the world, and the concern is that some of those citizens are going to do a bad thing in the future, and we don't know which ones they are because we can't tell the difference just by looking. They all sort of look the same, and so what we do is we come up with some sort of investigator whose job it is to determine who are the people who are going to do the bad thing, figure out who they are before they do it, and stop them. Now, the investigator knows that people like to communicate with each other using some sort of communication technology. That could be a telephone, it could be email, it could be some newfangled app on your phone. But in any case, when you do that, you're going to generate some record of that communication, which is managed by a communication service provider. And the investigator knows this, and the investigator, wanting to see who's communicating with whom in order to do the investigator's job, will go to a court and demand a warrant to get access to those records of the communication. And once the investigator has that warrant, will take it to the communication service provider and demand access to the particular records which are covered by the warrant. Now, this approach is problematic for a couple of reasons. First of all, the investigator's actions are not secret. The carrier or the communication service provider learns the scope of what the investigator is looking for, which means that if the investigator wants to be stealthy about how they operate, or is concerned about tipping off someone that they're under investigation, they have to trust that the service provider is not going to leak that information. The other thing is that if you're a concerned citizen, a third party who's not involved, you can't tell whether the scope of the warrant was followed in this process, and you can't even tell whether only valid warrants were serviced by the service provider, or whether there's some cozy relationship between the investigator and the service provider, which allows the investigator to see a lot more information than the warrant allows for. And also, the court can't ensure these things. The court just has to write the warrant and then trust that the investigator goes out and obeys the limitations in the warrant. And I should mention a sort of related but slightly different problem, which is that a warrant is really a kind of insider attack. So if you have the investigator who can go to the service provider and demand access to particular records, then that system also has the property that without the court, without the investigator, some criminal can go and pay a bribe to the service provider to get the same information. And so that's not particularly desirable. There's not a tight binding in the existing system between the policy decisions which are made by the court and the actual scope of the access that the investigator or anyone has access to. And so if we were to design a system for this problem from scratch, it would have a couple of desired properties. We would want to know that access to the stored communications records was limited exactly to the scope of court-issued warrants. And when I say access here, I mean compelled access. The service provider has all of the information in plain text, so obviously they can access all of it. Another desired property is that any access to the system is logged in some sort of audit record, which can be checked later for oversight purposes. Ideally, that log is encrypted in such a way that the audit record doesn't reveal what actually happened, so that the audit record is not itself a risk to the security of the system. But in an ideal case, even if the log is encrypted, you would like it to be the case that the third party can verify that the log contains the correct information. That is, it contains an encryption of the fact that a particular warrant was issued, and by sort of looking over the whole record, you can determine that the records which the investigator was given access to were exactly the same records as the court blessed for access. And a very simple protocol for achieving this is to say, okay, you have the service providers, and they're receiving records as customers make new communications, and they're going to take those records and they're going to encrypt them with a standard public key encryption scheme. And the ciphertext produced by this encryption will go to the investigator. The investigator will hold on to that ciphertext. The investigator does not have access to those records because they are encrypted. And the investigator does not hold the secret key under which they are encrypted. That key is held by the court. And when the investigator determines that a particular ciphertext should be accessed, the investigator would send that ciphertext to the court along with a request saying, you know, I think that this person is up to no good. I would like to review their records. Can you decrypt them for me? And the court will review that by sort of asking a judge who represents kind of an oracle as to what the policy is for access. And the judge will look at the request, flip a coin, whatever the judge does, and determine yes or no, this request should be, this record should be decrypted. If the judge says yes, the record will be decrypted and returned to the investigator. And the court will also write an encryption of that fact into an audit record. Now this satisfies all of the properties I gave above, except that we have to trust that the court only decrypts records when the judge says yes, and also that the court writes an encryption of the correct record into the audit log. And so it would be desirable to have a system like this, but that has some additional properties. One being that we don't have to trust any particular party to do anything specific, such that they can compromise the security of the system in an undetectable way. And then we would also like it to be the case that the audit record is, that we can, as a third party, a disinterested third party, can detach from the audit record the correctness of the audit record. And so we built a system that does that. It's a little bit more complicated. So here's the other system. What we're going to change here is we're going to change the standard kind of public key encryption scheme, or no, sorry, we're going to add, instead of the court doing the decryption, we're going to have special decryption authorities whose job it is to hold shares of the secret key. Recall, if we just moved the secret key out of the court to one decryption authority, that decryption authority would have the ability to just decrypt stuff. And so what we're going to do is we're going to use a secret sharing scheme to make it possible to share the key out over n decryption authorities, such that all of them have to participate in the protocol in order for a decryption to be successful. The second thing we're going to do is we're going to change the standard public key encryption scheme to a fancier kind of scheme called identity-based encryption, in which the ciphertexts are indexed not per encryption, but rather per something called an identity, which is just a string that might identify which service provider the record is held at, who the record pertains to, and when the record was created. That identity is then the thing that is used along with the public key to derive an encryption key that's specific to that record or that bucket of records. Records are encrypted under those keys and still held by the investigator. And then we took, there's an approach to identity-based encryption where the decryption can happen via something called blind extraction. So decryption in IBE requires extracting a decryption key that is specific to the identity that was used for encryption. And there is a blind extraction mechanism in which the court, by doing an interactive protocol with each of the decryption authorities, can extract their share of the secret key, but without actually letting the decryption authorities know which identity they are generating a key for. So that protocol is something that we took out of the literature, but the protocol we found in the literature does not generate any kind of audit record, so we modified it to build a new primitive, which we call auditable oblivious transfer, which is very much like the blind IB extraction, except that it yields an audit record, which can be written into the log as the protocol proceeds along. Once all of the shares have been extracted, the court can combine all of the shares and unblind them to get the secret key that is necessary to decrypt the particular record that the investigator wanted, and then send that back to the investigator. And there are some desirable technical properties that this system gives us. IBE is useful because it allows us to have a bunch of keys that are pertinent to more individualized records. So there's more tight coupling between the access control that's enforced by the cryptography and the access control decisions that need to be made during the operation of the system. It's also the case that the specific identity-based encryption that we use, the Boyen IBE, has the property that during encryption there is only modular exponentiation over an elliptic curve, which takes about 12 milliseconds per identity in the very slow version that we have. That could probably be made something like 3 times faster with some modest engineering. But even at this slow rate, that means that if you wanted to encrypt a full set of records for the entire United States at the granularity of 1 day, so you're going to bin all of the records for 1 day per service provider and group them together, or per customer per service provider. The number of encryptions that you would need to accomplish that with a modest amount of computer hardware, something like 1 rack of hardware, you're devoting less than 3 hours. So, it's achievable to deploy a system like this across a very large number of incoming records. And then this system has the property that we want, which is that we know that only the investigator can get access to the particular record that they've requested access to, and that access is only granted when a warrant for that identity has been validly issued by the court and validly recorded in the audit log. By including in the audit log a zero-knowledge proof that the key that was extracted is the same key that was requested, is the same key that was returned for the same identity, you can convince a third party in a trustless way that that the system has the information flow property that you want. So that system works when we have that's an example of a system that works when we know the property that we want in advance. In the real world, we don't know generally beforehand exactly what the system is supposed to do, because we have the problem that whatever process is telling us what the system should do hasn't given us a precise enough notion of what that is. And so that brings me to the second piece of work, accountable algorithms. And to explain this, I want to first tell a short story about an application of this system. And like any good story, this story is a story about the IRS. So if you are like me, you have just gotten together all of your tax forms for last year, and prepared them to make your tax filing. And come April, you will file your tax reporting, and the IRS will, for some people, say, surprise, you're being audited. They don't do that for everyone, but they do it for more than one person. But some people will just get their refund checks and be relaxed. You might expect that the audit decision that you get is based purely on your filing. But in fact, in the past, the IRS has been accused of using properties not just of the tax filing you've given them, but also of you as a filer. And in particular, they have been accused of unfairly targeting particular individuals or groups for additional scrutiny during the audit process. And in a scandal in 2012, in testimony to Congress, the now former IRS commissioner who resigned over this scandal said that there's absolutely no targeting of individuals that's improper or goes beyond the scope of the information that's available in the filing that people have given. That turned out to be wrong, and the IRS was forced to apologize for targeting people for properties of the filer. In this particular scandal, it was about corporate entities that represented particular conservative interest groups. The allegation was that the IRS was targeting these groups because they were politically opposed to tax compliance, and that made them inherently suspect in the audit process. And so that leaves us with a question: what does it mean in this example for the IRS's decision process about who gets an audit or who doesn't to be fair, to meet this standard of equal justice under law? And I'm going to set a fairly low bar here and just talk specifically about fairness in the form of procedural regularity, what a lawyer might call due process. And so that's going to mean a couple of very specific things. It means that everyone gets the same decision rule, the same decision policy. That decision policy was decided on in advance, so I didn't sort of predict what your tax return is going to say or what Ed's tax return is going to say and decide that the decision policy that you get an extra 100 points of audit interest if your adjusted gross income is within 10 cents of what I think Ed's adjusted gross income is going to be for last year. And then we want the agency making the decision to be committed to that decision policy, in the sense that they can prove later that they used the particular decision policy that they decided on in advance to make any particular decision for any particular person. And then the last property is a little different. It says that any randomness that's used in the decision process is fair. And what that means is that the agency did not improperly shop around for sort of the right random values, because any value that's chosen at random after the fact, it's hard to say that that value was, because it was chosen at random, any value you put there is as good as any other value. Except that what randomness is really giving you in a protocol is that you don't know how it's going to come up. So if the policy is we're just going to audit 1% of all taxpayers at random, you don't want it to be the case that the agency can sort of go off into the corner, shuffle the cards over and over again, and then pick their favorite 1% of people to audit. And I should say that all of these properties are very easy to achieve when there are no secrets and when the algorithm that is being used is totally deterministic. I don't know why Joanna finds that so amusing.
I found Joanna amusing.
I see.
I just suggested that if they picked the 1%, then that would probably be advantageous.
Right. Although, again, you might be able to get close to that just from properties in the tax filings. probably pretty easy to figure out who the 1% are from the tax filings. Anyway, to achieve this in a setting where the decision policy is deterministic and can be made public, you can have the agency take the decision policy and seal it up in an envelope, and then mail it out to a decision subject. When they get the envelope, they can hold on to it and send in their own specific input to the process. And then the agency will issue a decision, say, you're getting audited, and after the fact, the subject, being concerned about the correctness of this decision, can open up the envelope, look at the now revealed decision policy, and if this is an algorithm, that might be the source code for the program that implements the decision policy. They can then go to their computer, type in that program, type in their own specific input, and check that their decision is correct. The problem with this is that random algorithms are useful, and that secrets are also very useful in real protocols. And so in order to jump that gap, we're going to use some more fancy crypto. In particular, we're going to use two things, the first of which is called a zero-knowledge proof. Now, a zero-knowledge proof is a special kind of a proof where you sort of go along explaining something, and then I convince you somehow that the fact of something is true without explaining exactly how I know that. So I tell you that I know something without showing you what that thing is. A classic example of a zero-knowledge proof is this maze. So I might say to you, I know a way to get from R to S, but I'm not going to tell you how that is. You just think there's a wall there. And so what you do is you I go hide in the maze somewhere at either R or S, and then you tell me that I have to come from either R or S by flipping a coin. If it comes up heads, you say I have to come from R. If it comes up tails, you say I have to come from S. Now, half the time, I've hidden in the wrong place. I have to use my knowledge of how to get between R and S to come out the right place. A more general version of a zero-knowledge proof says that for some function, I know a value such that that function evaluates to true, but I'm not going to tell you what that value is. Now, a surprising thing is that there are non-interactive zero-knowledge proofs, and the general form of a non-interactive zero-knowledge proof is a single message in which I send you that message, and by examining that message, you learn that I know a value such that some function evaluates to true, but the message doesn't contain the value in question. It doesn't contain the witness. The specific instantiation of zero-knowledge proofs we use in this work is something which has a name that you can only love if you're a cryptographer. Something called a succinct, non-interactive zero-knowledge argument of knowledge, or a ZK SNARK. The SNARKs originated in a paper that has a very crypto-y name that is fairly recent, from 2013, and the paper is called Quadratic Span Programs and Succinct Non-Interactive Zero-Knowledge Proofs Without PCPs. PCPs are probabilistically checkable proofs. If you want to know more about them, you can go across to the CS building and ask their inventor, Sanjeev Arora, and he will talk to you at length about PCPs. And SNARKs work by taking that function that someone is executing, representing it as a circuit, which is why I have a circuit diagram here. And then via the magic of the crypto fairy, you turn the circuit into a representation which is possible to turn into a non-interactive zero-knowledge proof. And that non-interactive zero-knowledge proof is a single message, which is very succinct. That's where the S in SNARKs comes from. And succinct means that it's very small. It's at 128 bits of security, the proof is less than 300 bytes. It's 288 bytes. And it takes something like 5 milliseconds to verify the correctness of that proof. And that 5 milliseconds is constant time. It is succinct to send and verify this proof regardless of the complexity of the function that you're proving something about. The thing that does vary in terms of complexity is the time it takes to generate that proof. it takes something like minutes to hours to generate that proof, and a more complicated function is going to lead to a more time and resource intensive proving operation. The other important thing about SNARKs, which is so important that I put it on its own slide, is that in order to instantiate these particular non-interactive zero-knowledge proofs, you and I have to share a fairly large random set of parameters, which depend on the particular function that we're doing zero-knowledge proofs about. In order to get those random parameters, we need a trusted entity to come and generate them in advance, and then that entity just sort of goes away. They're not needed anymore for the protocol, but if they do remember some algebraic relationships between different parts of these random parameters, which are effectively like public keys, then they can create proofs of false statements. So we need to trust that entity to generate the parameters correctly, and then to forget everything that they knew about the random choices that they made in generating those parameters. Fortunately, there's a paper coming out this spring showing how to generate these parameters using a multi-party protocol, which has the property that as long as one person in the protocol is honest and actually forgets their portion of the random choices, then the whole set of parameters that's generated out of the protocol is trustworthy. And that means that if you don't trust me to generate the parameters, you can trust Ed instead, and if Scott doesn't trust Ed, then we can also include Joel, and if you don't trust any of us, then you can include someone else you do trust. And eventually you've reached a big enough set of people that that you can trust the whole set of parameters because you trust one of those people to act honestly. Now, the second piece of machinery I need is something called a cryptographic commitment. And a cryptographic commitment is a pair of algorithms, commit and verify. And commit takes any set of bytes, any digital object, and produces a short object called a commitment along with some randomness, a key. And if you feed the object and the commitment and the randomness back into the second algorithm, verify, it's going to give you accept or reject, thumbs up or thumbs down, that commitment is valid or that commitment is invalid. And the two important properties of commitments, without talking about how we construct them, is that the commit algorithm is hiding. So if I just tell you the commitment, you don't learn anything about what the thing that I am committed to is. And also commit is what's said to be binding, which means that it's not possible for me, after I create a commitment of something, to come up with another set of commitment and randomness or another object to commit to, such that I can run verify on those things and I will get accept. So that means that once I have told you the commitment to something, I can't sort of get out of it. It's sort of the digital equivalent of taking that source code and putting it in a sealed envelope and giving it to you so that I can't tamper with it. And so using those two things, we can construct a crypto protocol which meets our requirements. And it looks something like this. So first, the agency is going to take their decision policy, they're going to send a commitment to that to a skeptical user, who will then send back their specific input. And then if the decision policy is randomized, or in case the decision policy is randomized, the agency is going to accept an ancillary input from a random beacon, some extra bits which we just trust are random. Maybe they come from NIST runs a random beacon, but if you don't trust the government, you could look at the hash of the blocks in the last few blocks on the Bitcoin blockchain, or maybe you engage with the agency in some sort of fair coin tossing protocol. There are several of these. Or maybe you do trust some random beacon out there. You just trust someone to sort of spit out random data every 10 minutes reliably. And then once they have taken that random data, they issue their result. They say, oh, you're getting an audit. And when they issue the result, they also give you a proof, a zero-knowledge proof, that says this was your result, and that proof is specialized to your particular input. And that result is correct. It's the correct application of applying the decision policy we committed to to your particular input for the particular randomness that came from the random beacon. And for your neighbor, they will also give another proof which is specialized to your neighbor. And you can take this proof and you can go verify that it in fact matches up. So you can take a look and see that the proof corresponds to all of the things that you know, and that says that even though you can't see exactly what the decision policy is, you can see that your result is comes from the decision policy in such a way that all the things you would need to check to know that the result is actually correct have been recorded, and the proof sort of ties all of those things together in the right way. Now, if you're disappointed by your result and you want to challenge it, you can go and find some sort of oversight body, maybe a court, and you can take all of the things that you've gotten, the commitments, the proofs, the random input, and you can send them off to the court and you can say, is this result correct? And the court has the special power which you don't have, in that the court can go to the agency and issue some kind of warrant to compel them to return the actual decision policy that they use. The court can then review that policy for acceptability, decide, is this the right rule? Is this the rule they were supposed to be using? Are they really supposed to be auditing 2% of everyone who submits taxes, but with an extra 100 points of auditing for people whose adjusted gross income is within 10 cents of Ed's expected adjusted gross income for last year? The court can review the policy and also can take all of the crypto information, including some of the secrets that were available to the agency but not to an individual user, and take those that information along with the secrets to the crypto ferry, and the crypto ferry can then look at that and figure out, was the particular decision that was made consistent with the policy that was approved. So that leads us to the system having a bunch of desirable properties. One is that this commitment property, that we know the agency has a full explanation of whatever the decision was. They can fully explain how they got there, so that they can answer a kind of show your work demand later. And then you, as the person receiving a decision, can be convinced that the decision policy existed before the agency learned about your particular data, so it wasn't specialized to you. You can be convinced that the decision you got results from the decision policy that was announced early and was made available to whatever oversight body exists. And you can be sure that that policy was actually made available to the oversight body, that the policy that was used to make your decision is the same policy that the overseer or some internal committee actually reviewed for correctness. And then you can be assured of this fair randomness property, that the agency didn't, shop around for their favorite coin flip for you. A nifty extension of this protocol, which I mentioned because it doesn't require any changes to the protocol, just to change to the way that you instantiate it, is that for any property that you want the decision function of the agency to have, you can verify that property simply by expressing that property as a circuit over the secret part of the decision policy, and including that circuit in the function that you do the SNARK about. And so you can ask, for example, a more complicated question like, does the decision function discriminate against some protected group, or does it meet some particular formal fairness property? And there is an emerging but not enormous literature about formal fairness properties in machine learning, kind of big data decision making. And if you're curious about that, Cynthia Dwork, who is one of the leading figures in this particular area, is giving a colloquium Thursday,
Yes, Thursday, 12:30 over in Computer Science 105.
Yes. That is an option available to you if you're interested in that. I don't think she's talking about fairness in machine learning. I think she's talking about differential privacy, although she might bring it up and certainly would be willing to talk to interested people about it. The last thing I want to say about this protocol is that I am implementing it. It is moving along. I'm using a recently released piece of software. As far as I know, I'm only the second person to be building something on top of this, although I think that's probably wrong because there is a paper from a bunch of people at TU Darmstadt that I think may also be dependent on libsnark. So maybe I'm the third, maybe I was the second person, but they've beaten me to getting out into the world. It means that when I'm writing, I get to pass the awesome compiler option -l snark. The other thing I will mention about the implementation is that we use for pseudo-random number generation and for building the commitments that we need the new SHA-3 standard, which is advantageous because many of the operations needed to compute that are free in the particular funky constraint representation that you need in order to build a snark out of a function. That means that the overhead of the extra stuff you have to staple onto the decision policy to do the zero knowledge proof about it is only about 10 minutes of proving time. So that's actually pretty good. The last thing I want to say is that when we look at what does it mean for algorithms to be accountable, we think, well, what we should do is we should design processes that are fair. And fair might mean that a process is lawful in some way. It might mean that it's politically acceptable. It might mean that it's consistent with some set of public values. And that's really an ideal. It's hard to define what fairness means. Accountability is a different option that's available to us. And in accountability, what we say is, we can take these decisions about what is lawful or what is politically acceptable or what is consistent with public values, and we can sort of package them up and defer them, and then we can designate someone as the decider. Someone is an oversight body, the Congressional Committee on Algorithmic Decision Making, or whatever it is, the Joint Committee on Credit Score Fairness, or the Consumer Financial Protection Bureau. And you can say to someone, well, we don't know exactly what the right thing is, but we can tell you that if we have to show our work to this person who is responsible for figuring out what that is, then we are in a position to do that. And so that's achievable with current technology. One of the interesting places that this work is going is to figure out exactly what particular applications would look like for these techniques that would make sense in the real world. Once we know that, then we have a nice set of tools in the toolbox to say that when you design important processes in public context, that you can design those processes with the idea that you should be able to convince some skeptical participant or third party who's not a participant that that process is accountable in the way you want. And with that, I'll take any questions that the audience has.